guys can see my screen, right? You can see this thing that looks like Africa a little bit. All right.
Yes.
All right. And the continent of Africa. All right. So then we have something that's hot and something that's cold. So the hot temperature here, let's just give it a temperature. Let's just say it's T hot, TH. And here it's TC for T cold. So what's going to happen is temperature travels from hot to, or heat travels from hot to cold. Right. So I'll say this is heat right there. So heat is Q. Heat could also be Q like that. It doesn't matter. You know, just know that that's heat. This is with conduction. It's usually solid to solid. But it doesn't have to be. You can have, because what happens is the next one handles anything that's a fluid or a gas, or a fluid, a gas or a liquid. But usually it's solid to solid, and when they're touching, they conduct. All right, so there is a homework problem. The equation for conduction, let's say it's heat transfer is equal to heat. So little k is called thermal conductivity times the area divided by the distance, which you call delta x, times the temperature difference. What's the temperature difference between hot material and cold material? So that's how you determine what this little, let's just call it, for now, let's just call it lowercase q, right? So heat travels from a hot substance to a low, or a hot solid to a low solid. And so the area is this interface here where it's touching is the area. And then dx is basically just, you can say center of gravity or the distance that the heat needs to travel. We'll call that delta x, right? Like that. Okay, that's conduction. Convection, you've probably heard all these terms before. Convection is equal to the heat transfer. So here's it's usually between a solid and a liquid, or a solid and a gas, so a solid and a fluid. So I'm going to say, let's call this a solid here. And let's say it's also hot, so I'm going to give it a red temperature here, or a red color for the temperature. And then I'm going to go back to my pen here, say T hot. All right, so it's solid though. Say solid, just to keep it. Now you have a fluid flow. You have some flow going in. There's a fluid that's flowing over this rock, and it has a temperature. So it's a fluid, and the temperature, just say it's C for cold. So that's what convection is. Whenever you have a fluid going over a solid surface, and it removes heat that way, right? Then it's convection. All right. So the difference is that you need a fluid. So it's a mass transport problem. So the fluid starts off kind of its own temperature here, and then starts to pick up some heat. So that's where my red dotting is. It starts. So the temperature of the fluid is a function of how much surface area it went over. So then the area of the surface is basically whatever the fluid touches. Right. So that is the area right there, A. Now let's do the equation for that. So Q is equal to the heat transfer coefficient, which is pretty much just a fudge factor. I'll tell you about what that is later. Times the area that we just traveled over, the fluid travels over, times T hot, this hot surface minus the cold fluid. TH doesn't have to say H, could be T, it could see T object, TI, TO, and TC could be T media or TF for fluid, right? But basically it's a hot to cold, right? Whatever's hot, whatever's cold. You put it like that. And that's what your heat transfer through convection in. So the units here, this is in rate. So this is actually the units in kilowatts. I didn't mention this in my other class. Hopefully it doesn't have any confusion here, but the units are kilowatts. Because there's rate already, the rate is based on this material constant there. It's called thermal conductivity. And the rate here is the heat transfer coefficient. So the heat transfer coefficient is a function of the fluid, basically. It's how well the fluid flows over this thing. So for example, there's another thing called free convection. So this is called forced convection. Because the fluid is kind of being forced, whether it's the force, could be the force of a river. This could be a stone on the ground that's hot relative to the river temperature, but it could also be you have a pump and you're pushing fluid over the solid. But in reality, and regardless, it's being forced over this solid. But you can also have what's called free convection, right? So you can have fluid flow this way, just caused by the temperature. This is kind of what causes weather temperature phenomena, right? So this could be T hot right here, and then the fluid could be T cold, and this is called free convection or natural convection.
Professor?
Yeah.
When you say fluid, you're talking about liquids and gases, correct?
Yes. Yeah. So fluid can be a liquid or a gas. Yeah, it doesn't have to be. I know I keep saying liquid because I'm thinking, but it's fluid. It's a liquid. It could be air. This could be air here, and it's air. What happens with air is that it so if this is a hot temperature, so air comes like this, right, and it starts off cold, and when it hits a hot surface, it rises, right? It immediately rises. Because hot air rises, right? Because the temperature of the air it's blue, and then it starts to pick up heat from the hot solid there, and it rises. So what happens when it rises? It doesn't create a vacuum, right? So more cold air comes in its way, and so what's happening is you always have fresh amount of air that's cooling something because hot air rises and moves out of the way. Imagine if hot air didn't rise, right? I don't think we'd be able to breathe, right? I don't think if hot air doesn't rise, this hot rock would just keep getting hotter and hotter. For example, if this was your laptop, someone in the class mentioned that the laptops heat up more with Zoom. Then if there is no air rising, what happens? The air basically just stays here, and the air starts to get hot. Your laptop just keeps getting hotter and hotter, and eventually it'll just start to melt down. But this is called free convection. But regardless, it's convection. All right. Any questions on that? Heat transfer coefficient, again, it's just you can look. There isn't any heat transfer. There's no convection problems, but it's basically a function of flow. So, for example, the heat transfer coefficient for I'm going to say for free convection, which is what I just drew here on the left-hand side, is less. It's going to be smaller than the heat transfer coefficient for forced convection. So I'm going to say force. That's because they're both with F, right? So I'm going to say with forced convection. So free versus forced, right? So this one on the right here with the fluid going over it from left to right, that one has more ability to pull heat than the natural convection, because natural convection doesn't, right? You don't put a fan in front of it. All right, the last one, start a new page here. The last one is radiation. So radiation. So I erased but we can go back to what do we mean by radiation? Well, it says right here, radiation, the transfer energy due to emission of electromagnetic waves or photons. What does that mean? Photons or electromagnetic waves? Well, it means that this could be a vacuum here. It doesn't have to be, but this could be a vacuum. Since I like to work on space projects, this can be space, right? You're out. You're in outer space. There's a vacuum, right? Well, how does the sun warm us up? The sun warms us up through radiation because it's in a vacuum. There is the last two examples I gave you require a medium, right? So conduction requires a medium, which is solid, the solid material from one solid material to another. Convection requires a medium between one solid hot material or cold material and a solid fluid. Well, I'm sorry, it's not solid fluid, but a fluid, but it's material. It's one from one material to another. So it does require substance, right? So how do we get heat transfer from vacuum, right? There is no substance. There's no gas here. There is, well, not significantly. There might be some hydrogen, helium, but it's not enough to provide heating and cooling. So so the way it does it is through radiation. And so I'm going to say this is T hot. And then what happens is we get photons are coming off of the surface of the, and they're, photons are basically energized particles or wave. They behave, they're massless particles of energy that travel off of the surface, right? And then over here, you have something that might be cold. So for example, let's just say, right, something that's much colder, like the Earth, right? So right here, it might just be easier just for me to type. Right. So Earth is there. Let's try this again. I have to hit enter. All right. And so the temperature here of Earth is much colder. So I'm just going to say TC. So heat travels from hot to cold, but if there is no vacuum, I mean, if there's a vacuum, and the only way heat can travel is through radiation. And so the equation for that is equal to emissivity, because this is emission, right? These are photon emissions, so there's a value here called emissivity times the area times something called Boltzmann's constant times the temperature difference of hot minus temperature difference cold, but it's to the fourth power. Okay, radiation. Radiation is about 90% of the heat. So if you're an aerospace student, you're going to need to be an expert in radiation, because if you're putting anything in outer space and if you're doing any thermal heat transfer, it's a big component, right? Because you can't, there's no medium in space, so there's no convection, is zero. And then there is conduction, but that's kind of internal to your spacecraft or to your vehicle. But the way you expel heat to the environment or absorb it is through radiation. So emissivity is interesting. This is E. And it's usually between 0 and 1. So it's any value between 0 and 1. And then, for example, if something is more emissive, or it works in reverse, emissivity helps an object emit heat. It also helps absorb. So a black shirt, for example, has an emissivity roughly equal to about 0.9. So it's almost 1. It's almost a perfect black body, or it pretty much absorbs really well. So if you wanted to absorb the heat from the sun, you wear a black shirt. Just say, I don't know, if the sun's out somewhere and it's just a cold day, you want to wear black. Black also helps emit. So this Sunday is supposed to be 100 degrees. As long as it's dry outside, and if you're going to be in the shade, wear a black shirt. It'll cool you down. better than a white shirt. So the emissivity of a white shirt, for example, is about 0.2 or so. So therefore, what happens is if you're in the sun, you want to wear a white shirt, right? If you're, especially on a day that's hot, you don't want the sun to, you don't want to absorb heat by the sun, right? So you wear a white shirt, even a white, what do you call those? A windbreaker or something like that will help you a lot. So again, but if it's hot outside, you're going to be shaded somewhere, and you want to cool down, you don't wear a white shirt. I mean, you're okay with a white shirt, but you actually get more cooling if you wear a black shirt in the shade. And that's kind of something it's non-intuitive, but it's true. Okay, any questions on this? All right. Let's go back to the slides.
Professor.
Yeah.
What you were saying about the black and white shirt like being soaked in the sun, that's considered true though?
Yeah.
Oh.
Yeah, no, absolutely. So is it not obvious to you guys, or I mean, so we know that so a black shirt, right? So we know that for a fact, right, is going to absorb heat, right? So you got a black shirt, we know that, right? We know that the sun is going to, attract. It's almost like it attracts sun particles, right? Gets hot, right? So we know that for a white shirt, right? So, sorry. I mean, this is kind of fascinating. So for a white shirt, it's also, what's happening is these things here, they basically get like, almost they get reflected off, right? So this is then you end up kind of being cool, right? So I would say it's not necessarily true, but so you're cool. However, black emits heat as well. So when this thing gets hot, it also, if you have a black shirt, it also wants to get rid of the heat. That's why tires are black, right? They're painted black on purpose to keep them from overheating. That's why radiators, right? A radiator doesn't make any sense in your car to be white. This works both ways. It's a dual direction situation, right? So if you want to expel heat or absorb heat, that's the bad thing with black. It does a good job in both absorbing heat and repelling heat. So a radiator that's under your hood is really never going to see the sun. So you want it black so they can actually just get rid of the heat. However, white shirts can't really get rid of heat. It's like a little bit, right? It's not. It's like not really. Right, it doesn't have a good if what I'm saying is if you're in the shade, right, and if it's a hot day outside, what's the chance that you're going to be in the shade? I don't know, but if you're in the shade, just say you're just working in the shade, you want to wear a black shirt, okay? Take my word for it. If you're going to come out in the sun, I mean, again, if you're outside, right, chances are you're probably going to stop and pass by in the sun, so you'll probably want to wear a white shirt if you're in the sun. But if you're in the shade, wear black. You'll actually be cooler.
Never thought of it that way.
Yeah, and it has to do with emissivity. The emissivity of, again, if you do the calculation and you use this equation, you're just say that there's a hot surface outside. The sun is about 3,000 Kelvin. You're like about, I don't know, 370 Kelvin or something like that. Just do the calculations. This has a big part of it. Yeah, so black shirt, white shirt. Polar bears, right? They have white fur. But they also have black skin. So they have kind of a duality there. I'm not really sure how that works, but yeah, it's kind of a fun fact. Let's go back to our lecture. All right. So energy transfer, this is just going to be sign convention. Fine, you. All right, so sign convention. I have a box. Do I have the ability to do dotted lines? No. Okay. Well, that's kind of a dotted line, but it's going to disappear as soon as I start drawing on it. So let's say we have a heat, heat could come in or come out, right? So Q, and I'm going to say this is called heat. So right here, the title is going to be sign convention, which means how do we define, is it negative or positive, right? So if heat comes into a system, it's heating up the system. So the system, it's basically, what does the system see here, right? So the system sees heat coming in, so it's positive. If it leaves, it's negative. So that's pretty straightforward, right? So if heat leaves the system, it's negative heat. If heat enters the system, it's positive heat, right? So you put a negative in front of it if it's leaving. If you leave it positive, it's entering the system. Work is different. So this is energy in terms of work, right? So it's W. So work can be mechanical work, right? It could be you're turning a paddle. But usually it means electric work, or it could mean no, it could mean you're turning. You have a crankshaft. This could be a piston chamber, and you're pushing a piston in this chamber. You could be pushing that piston, and that's work you're putting in. You could be extracting it. That's work you're getting out. For work, when you push a piston and force work into the system, it's negative. When you extract work, it's positive. Right. So think about it in terms of, and this is just sign convention. You could do your own convention and reverse this. Then you'd have to reverse heat. It's just that heat and work in different ways. So the best way to look at this for work is the system is lazy and you need to put work into it to get it to operate. Or the system is productive and you can extract work from it, right? Probably best example is hold on a second. Probably the best example here is a piston in a chamber. So we gotta, we'll do that black. Then we do a blue piston here. And it has, so it has a shaft or something that we can take work out of. All right, so I have the bad habit of pressing escape. All right, so if you put work into the system, so you can, right, you're pushing the piston in, then you're creating positive work. If, for example, there is an ignition here like your car, and the pressure increases dramatically, right? The pressure through a spark plug ignition and the gas explodes. Sorry, my screen just turned off right now. Then then work is gonna push the piston out, and you get to. I'm sorry, did I say positive? Someone should have caught me. I messed it up. If we're putting work into the system, then it's negative, right? If we're getting work out of the system, if, for example, the pressure goes up due to an ignition in your cylinder, then it's positive work. So then you would put W, then you put positive. Okay, that's just sign convention, right? Next slide. All right, energy transferred by work. All right, so when we're talking about work, let's go back to our slides here. All right, so I got my black pen, got a line here. Just because I have a hard time drawing straight lines. All right, so on my vertical axis here, just say I have pressure. My horizontal axis here, I have volume. All right, pressure and volume. The example could have been that piston. I should have made a copy of it. But So just say we start off here at state 1, and then we move to state 2. And what that means is that state 2 is just, state 1 is basically you got a high pressure here. So say pH, and state 2, right, is P low. So you have a process that you go from a high pressure and a small volume, which we call V1, and here then we drop to a low pressure and a large volume, which we call V2. So again, case in point, that would be again, the perfect example is basically a piston chamber, where you have a piston inside of a chamber, and you're doing that. All right, so let me see. So then what happens is you have the ability to move this thing in and out, right? Move this piston in and out. All right, so maybe you start off at a high, high pressure, low volume, and then you move this piston out, right? So now you go from point 1, maybe it was originally here, right? Your piston was originally here, and that was state 1, and now it's at state 2 when you moved it out, right? Or you allowed it to move out to state 2, and it moved it here. So therefore, it went from a high pressure, if this is gas in here, right, the temperature will drop when you do that. So it goes from high pressure, low volume to a low pressure, larger volume. So the reason I tell you this, it is important to know when you do a calculation, for example, what is the work associated with that, right? So the question here is, what is the work associated with moving that piston going from here to here, from 1 to 2? It's not enough to know the end states. It's not enough to know pressure. You need to know the pressure, the high pressure, and you need to know the volume 1. But you also need to know how you got there. What's the path? Let's see if I can do this. So was it a straight line? Did I go from 1 to 2 like that, or did I bend like that? Right. It makes a big difference. Did I go for like that? Did I do did I do a straight line, or did I actually let's see, do a different color here. I'll do green. Or did I have something like, oh, that looks pretty weird. But regardless, those are the different paths that I could have taken to get from 1 to 2. So we can call this A. Might as well do it in the right color. Path A, path B, and path C. Right. The reason it's important is because I'm not sure if I told you this already, but work is actually the integral of these paths, basically going from 1 to 2, state 1 to state 2, the integral P dV. Right. So basically what it is it's basically the area under the curve, right? And it's dependent on your pressure, the path of your pressure, right? So the pressure isn't constant, it's actually changing. And so therefore it is the integral of these 3 conditions. So if you look at the integral, it's the area under the curve. So it makes sense that work A is less than work B, which is less than work C, because work C has the largest area under the curve from 1 to 2. So the path, so if you were building an engine, and this was your positive displacement of your engine, this was what you were going to generate, then you were going to recoup from your engine, you would want C. You would want more work for whatever input work you put in, whatever gasoline you put into your car. You would rather have it to come as path C, right, from 1 to 2. you would rather go from 1 to 2, give you C, than give you A, because it gives you more. It's actually the area under the curve is larger. So for work, for work C, it's the path that P took, but the C path. All right, so this is for work and heat only, for energy. It's not enough to know the end states. It's not enough to know the P1, V1, P2, V2. You need to know the path. Okay, keeping an eye on the time here. If there's any questions, please let me know. All right, now here we go. I'm gonna go ahead and steal this. Hold on a second. Steal this image here so I don't have to draw it. Right. Great. I don't want it over there. Here we go. All right. So let me make sure I have my pen. All right. So here, what are we looking at here? We're looking at. Let me look at my slides here, so I don't have to go back. All right. Electric work. We're talking electric work. Okay. Yeah. So I had mentioned before that we only care about what crosses the control volume. So I'm going to make this like a light blue base. Let's just assume that's a dotted line. I'm going to call that my control volume, or my control, say control boundary. So what I mentioned before is we only care about what crosses that boundary. So what I have crossing it right now, this is just a label, nothing, it's not crossing here, but I have electric work, right? That's coming in. There's electrons coming out, but basically the electromotive force, the electricity is coming in through one area, and that's right here, right there. So just go, right, it's coming in like that. And even though it's giving off heat inside, I don't care about what's happening inside here. I only care what's crossing my boundary. So again, I only care about what's here. I only care about what occurs right there. That's my only point of concern, is what crosses there. And what I have is electricity's crossing in there in the form of work. And so this is really important, but this is kind of electric work, right? Sorry. So electric work, this is way too large, is equal to my voltage, right, which is there, times my current. Well, actually, W dot, my work rate. So it's basically going to be measured in kilowatts, right? And so, yeah, there's a resistor there. So how do I equate it to my resistor? Well, it turns out that voltage is also equal to, you can convert the power is also to V, voltage squared divided by the resistance, using Ohm's law. And so if I know the voltage and I know the resistance, I know my work rate in kilowatts. Okay. Really important when you're creating heaters, right? So as a spacecraft design engineer, I use patch heaters, where they're these kind of electrical heating patches that I put all around the spacecraft on surfaces to keep them warm, because space is cold, especially when you're in the shadow of when you're going around Earth and you go into the shade, right? You go into the nighttime, it gets really cold, and so sometimes you need electric power to keep the spacecraft from getting too cold and damaging electronics. So I do this all day long. Given the resistance of my patch, given what's my bus voltage of the spacecraft, I can determine how much power I basically sized this resistor here based on the I order resistors or patch heaters based on resistances that I, to keep my spacecraft warm. Okay. Moving along, that was the word on heat transfer by. So do you guys understand though that this is not considered heat, right? This is not considered heat, right? It's considered work. Now heat may transfer here, right? But I don't care about, this is inside. I don't care about what's going on inside, right? So for example, let's do an example. So one of your examples in the book has a box, and inside of the box has, I guess I can use, basically has a candle. Let me see, the base of the candle is like that. And then maybe I can use this as, right. All right, so there's a candle in here. Oops, maybe I can do black. So my candle is lit here, and then what happened is I have for my box. Let's see, for my box, it's well insulated, right? So let's just say let's call this like blue insulation, and it's really well insulated. Oop. So it's perfect insulation to the point where there is no heat transfer across the surface. So no heat transfer. So basically, Q is equal to H. Remember, Q is equal to 0. So find what's my change. Let's see. So given that, what is the change of the internal energy of the box inside the. So that's the question I have for you. Right. What is the what's the change of internal energy in the box? Right. So internal energy, if you guys don't remember, is it's basically I think it's U, and so I'm looking for the change of energy in the box. What we could do is you could say, well, what's the, so I'm looking at, so all right, so what this is equal to it's the change of heat crossing the boundary minus the change of work crossing the boundary, right? That's what's the change of my internal energy. This is the equation for any energy change inside of here. Because there's no potential energy change, there's no kinetic. The only thing that's changing may be the temperature inside, right? But I don't know what that is, because why? Because I don't have anything crossing my boundary. So the question was the box, right? They didn't ask about the candle. They didn't say what's the internal energy change of the candle. It's asking about what's the internal energy inside the box. So therefore, I need to know what crosses the boundary here. I need to know what's my Q and what's my H, or what's my Q and what's my W. Sorry. Well, I know Q is equal to 0, and last I saw, there is no electricity put in here. There's no piston. There's no paddle. So this is 0. So therefore, this is 0, and this is 0. Therefore, my change of internal energy is equal to 0. That's it's one of your example problems. I think it's example 2-3. So relative to the box, there is no change of internal energy, but it's a little bit non-intuitive, because you're thinking, well, there's a candle burning in there. What do you mean it's not? There's no change. The candle will eventually burn out, right? And so therefore it'll probably So what's happening is if it's perfectly insulated box, the energy never gets to escape. So yeah, the candle may burn out, but it'll just manifest itself as hotter environment or hotter air or whatever. And so since there is no energy coming out or in of the box, therefore the change of internal energy is equal to 0. And I only care about this, ladies and gentlemen. That's all I care about. Any problems? If you ask me to characterize the energy change here inside this box, I'm only going to look at what crosses the boundary. It's different if you ask me what's the change of internal energy of the candle. Then therefore I gotta draw a box here. Right, I gotta put my box in becomes here. Put it in here. But you didn't ask me that, or that's the question. That wasn't the question that was posed. So then I have to actually draw the diagram around the candle and then figure out, the temperature of the candle before and after, that kind of thing. All right, so we got 6 minutes left. And this is kind of where I left off at the other class. This was my last example. Yeah, so you guys have any questions? We can open it up for questions now. You guys have any questions?
Professor, do you mind just saying again what delta U is?
Yeah. So delta U is the it's the change of and so this is the internal energy. Internal energy. And that's usually characterized by change in temperature. But again, I'm being asked to find the change of internal energy of this box. And so, when we do any energy, and I kid you not, this is something that you have to remember when you do an energy analysis of anything, you look at what's crossing the boundary. Is there heat crossing this boundary? Is there work crossing this boundary? The fact that there's a candle in there doing something, there could be a nuclear bomb in here for all I know. I just need to know through the problem statement what's crossing my boundary, because it was asked. The example in the book says find the change of internal energy of this box, because you didn't give me any heat transfer. Well, there wasn't any, because it was what was given to me is that there is no heat transfer. So that was explicitly stated in the example. If you would have said, well, I don't know what the heat transfer is, but yeah, there is heat transfer there, then I can't solve the problem. But if you told me explicitly this thing is perfectly insulated, then heat cannot transfer through the boundary, and work is not existent here. There is nothing showing that there's electricity coming in or out. Therefore, the change of internal energy of this box is 0. Okay, so it's internal energy.
Professor?
And yeah.
Oh, sorry. Continue. Sorry.
Yeah. Go ahead. Yeah, go ahead.
Well, I was going to say pretty much what do you mean by insulated energy? Just what's inside?
So so the weird thing is that since this is a perfect insulation, so the problem I gave you was that this is given right here. Given no heat transfer at, well, I should say at boundary. Right. So there's no heat transferring. So therefore, the temperature of the inside here stays constant, because there's no ability for the energy to transfer out. I don't know if
the temperature inside the circle.
Yeah, inside the box.
Okay.
So I want to know what's the change of the internal energy inside the box. And what I'm saying is that the box is defined by this blue. Really, there's a boundary here, right? I put a dot all the way around, and then again, if I'm doing an energy analysis, I need to know what's coming in, what's coming out. Well, nothing's coming in, nothing's coming out, because by definition, no heat transfer can happen across the boundary. and there is no work, so therefore there is no internal energy change to the box. So for example, if the box started with 1,000 kilojoules, once the candle burns out, it's still 1,000 kilojoules in that box.
Okay.
Okay, that's what we're saying, internal energy.
And also with what you were saying about internal energy for delta U, could that also be considered as potential energy, or no? Is this completely different?
No, that's different. So yeah, and the total energy is basically internal energy, right, plus kinetic plus potential. So those are separate.
Okay.
Right. So I basically just said, it was asking what's this part right there. Right. So the assumption is that there is no kinetic and potential energy. Well, regardless, there isn't any crossing the boundary. So those are assumed to be zero.
And
so,
how would you know that it's crossing the boundary then?
They got to tell you.
Okay.
It's got to be told to you, and usually it tells you that heat's leaving. The problem might say something: heat's leaving at a rate of 2 kilowatts, and work is being added at a rate of 1 kilowatt, right? And then that's how you know.
Okay.
But they specifically told this is adiabatic. There's no heat transferring, so therefore we know. And since there's no work, that we know that's what the equation basically comes out to, right? All right. Okay. Hopefully that answers that.
Thank you.
All right. You're welcome. All right. Any other questions? So if there's, go ahead. Anyone want to? Okay, so it's 8 o'clock. I'm going to stick around for half an hour if you guys have any questions. The rest of you guys can take off, and thank you for attending. And I guess we're gonna keep teams for now. There was a big push by 2 students at my last section to transfer to Zoom. If you guys rather me go to Zoom, send me an email or send me something that says, "My goodness, I'm tired of this stupid Teams thing." I know some of you guys were having a hard time getting in, but maybe we can solve your problem, right? Maybe we can work it out. So for now, I think I'm going to keep, at least for this section, I'm going to keep Teams. All right. Thanks for attending, and I'll stick around if there's any you guys have any questions or. Okay, I'm going to stop the recording.
Have a nice weekend, Doctor.
All right. You too.